Quantum computing looked like a snail's race for the past year, but suddenly a lot has happened at once. It seems like commercially relevant quantum computers might be here faster than expected within just a few years. And they're becoming dangerous faster than expected. Let's have a look. The first major news of the week is that IBM has unveiled a new plan to build a commercially interesting quantum computer from superconducting circuits. In the past years, they developed a new error-correcting algorithm that they say drastically reduces the number of physical qubits needed for error correction. You see, qubits make errors, so what one does is one creates a redundancy with more qubits, and by help of this, one can correct the errors. That way, one can combine many physical qubits to one logical error-free qubit. But this means one needs a huge amount of physical qubits to build a useful quantum computer. IBM now writes that their improvement cuts the required overhead by approximately 90%, which is huge. With this, they want to be able to deliver 200 logical, so fully error-corrected qubits by 2029. And a few years later, they want to have 2,000 logical qubits. This would be well in the territory of commercially relevant applications, which have been estimated to become feasible at about 150 logical qubits. IBM still faces the problem of having to scale up their platform from currently a few hundred physical qubits to a few 100,000, and the press release says nothing about how they want to get this done. However, their goal has come 90% closer. The company PsiQuantum also has plans to build a commercially interesting quantum computer. However, they use photonic qubits, which have been far less studied and are less understood than IBM's approach. Now, add to this the next big quantum computing news that comes from a preprint that recently appeared on the archive. The author, Greg Gidney of Google Quantum AI in Santa Barbara, argues that quantum computers will be able to break RSA encryption much earlier than anticipated. Breaking this encryption is one of the key applications for quantum computers. It's one of those tasks where the devices should, theoretically, be able to dramatically outperform conventional computers. Up until now, we assumed that RSA breaking would only become possible after other applications, for example in quantum chemistry, become feasible. That is, we'd at least have ample warning. But if the new paper's right, that won't be the case. This is because the author of the new paper says that quantum computers with under 1 million noisy, so not fully error-corrected qubits, could already factor 2048-bit RSA in roughly a week. This is a significant reduction in time compared to earlier estimates. Indeed, the same researcher estimated in 2019 that the task would take 8 hours with 20 million physical qubits. It's not that the earlier estimate was wrong, it's just that since then, algorithmic improvements have much reduced the computational burden. And that doesn't take into account the IBM error correction improvement. If these estimates are both correct, then we'll see RSA broken before 2029. That quantum computers might be able to break RSA is a big headache because it's been used to encrypt digital data for decades, and that includes a lot of confidential, high-stakes information. While the world is about to switch to encryption protocols that can't be broken with quantum computers, the so-called post-quantum cryptography, it's highly likely that intelligence organizations are in possession of sensitive data which they currently can't read. All that will become readable if they have a big enough quantum computer. The political consequences could be dramatic. And the third quantum computing breakthrough I have this week is that researchers from the University of Oxford report a new world record in the quality of their qubits. It's a stunning 1 error in 6.7 million operations. The qubit in question was a trapped ion, so it's yet another different technology from that of IBM and PsiQuantum, but this too serves serves to show that the technology is developing rapidly. In other news, the CEO of the quantum computing firm IonQ, who has been highly praising his company for months, sold all his stocks. Personally, I'm still skeptical we'll see useful quantum computers in the coming decade, because I suspect that the more qubits they'll try to combine, the more they'll push the system into a chaotic range that will become difficult to control. When will quantum computers finally become useful? We need a quantum computer to find out. Where does gold come from? This question, it turns out, is surprisingly difficult to answer, but a new observation seems to now have solved the mystery. Let's have a look. The chemical elements that we find on Earth all have a long history. The lightest of them, like hydrogen and helium, were produced directly in the early universe. The heavier ones are then created from nuclear fusion going on in stars. However, there are a few elements which we have on Earth that nuclear fusion does not readily produce. Those are gold, platinum, uranium, and a few others. Their formation requires rapid neutron capture, which is called the R process. This requires an extreme environment rich in free neutrons and high temperatures. For a long time, astrophysicists thought that these elements are produced in supernova explosions. The idea was that the collapse of the iron core blasts out nuclei and neutrons at such a high speed that rapid neutron capture becomes possible. However, over the years, detailed models showed that this blast wouldn't have sufficiently many neutrons and also didn't move quickly enough. It just couldn't sustain the rapid neutron captures needed to produce nuclei like gold and platinum. The idea that supernovae produce gold has by now been mostly abandoned. Don't you feel so much better knowing that sometimes even a supernova isn't energetic enough? Astrophysicists then thought that the heaviest elements are produced in the collision of neutron stars. Neutron stars are the remains of some supernovae explosions. Sometimes it happens that two of them end up orbiting around each other. These binary systems slowly lose energy by gravitational radiation and spiral into each other until they merge with a burst of gravitational waves. This creates the right conditions for the R process, because when the stars collide, they eject extremely neutron-rich matter that decompresses rapidly. This gives small seed nuclei access to vast numbers of free neutrons. This hypothesis was directly confirmed in August 2017 when LIGO and Virgo recorded gravitational waves coming from such a merger. Telescopes then looked at the light coming from the location in the optical and infrared range. They found evidence that R processes must have occurred and calculated how much of each element the merger would have produced. They found that the event had produced 3 to 13 Earth masses in gold. It was the first direct proof that smashing neutron stars are major gold factories, and a reminder that physics still makes progress. But that doesn't entirely solve the problem. The issue is there just aren't sufficiently many of these neutron star mergers. This is especially obvious in the early universe, because it can take billions of years in which stars in a binary system circle around each other until they finally merge. Yet, astrophysicists know from spectral analyses that some of the earliest stars already contain gold. So where does that come from? This is where the new paper comes in. These astrophysicists say they found another source for gold. That is another way to do these R processes. And this is giant flares from magnetars. Magnetars are neutron stars with super strong magnetic fields that can reach up to 100 billion Tesla. Occasionally they erupt in flares, much like our sun, but so powerful that they briefly outshine all other galactic X-ray sources. The physicists say that these flares blast off a small amount of the neutron-rich crust into space at enormously high speeds, and that creates the right environment environment for rapid neutron capture to take place. And it isn't just a theory. They have data to back up their idea. They looked at data from a 2004 flare that came from a magnetar in the constellation Sagittarius. It's on the other end of the Milky Way, about 40,000 light years away from us. This flare had a delayed glow of gamma rays lasting several minutes. It was too faint to directly look for signs of gold because that would have been produced in comparably small amounts. However, they did find evidence of nuclear decays, which strongly suggests that our processes must have occurred. This means that gold and platinum would have been produced as well. Now, a magnetar flare produces far less of these heavy elements than a neutron star merger, just because there's less material involved. But unlike neutron star mergers, which are rare occurrences, flares happen pretty much all the time. And they also started happening much sooner, already after the first supernovae left behind neutron star remnants. The researchers estimate that over cosmic history, these flares have contributed around 1 to 10% of the total galactic inventory of heavy elements, enough to explain the early gold seen in ancient stars. So the new picture is that most of the gold and platinum we have on our planet comes from neutron star mergers, but a tenth or so comes from the magnetar flares. The universe is full of surprises. You think a star is just sitting there being dense, and then it throws gold at you. And now that material is hanging from someone's earlobe in a disco. Do current AIs have free will? A philosopher just argued that yes, they do. You might say, well, who cares what some philosopher says? And in any case, this isn't a question for a science channel. But I think this is important for practical purposes and not just philosophically. With artificial intelligence, we're creating new beings. Free will is a sign of agency, and we take it as a condition for moral responsibility. Whether AI have free will, therefore, determines whether we can hold them responsible. We better sort this out. Free will is often described as the possibility to have done otherwise, but that otherwise possibility must have been of your choosing. But based on this definition, there's no such thing as free will, because our decisions are almost entirely determined by the laws of nature, except for a random element that comes from quantum effects. This is true for us and also, of course, for AIs. So yes, this haircut was probably inevitable, but on the bright side, not my fault. The laws of nature did it. Case settled? Personally, I indeed take this to mean that free will just doesn't exist, end of story. However, philosophers are instead looking for other definitions of free will so that it's compatible with what we know about the laws of nature. This is called compatibilism. There are many different flavors of free will in compatibilism, but they have one thing in common: agency. And since we're now entering the age of AI agents, it makes sense that we discuss the question of whether the agents actually do have agency. How much agency a system has depends on how much of its behavior can be predicted from external input. The more predictable, the less agency. The behavior of a toaster, for example, is strongly determined by external input. You push a button, it toasts. Therefore, philosophers would say a toaster has no agency, it has no free will. If you push a human being, results are varied and only rarely toast. So humans have a lot of agency. But it's not like philosophers agree on exactly how this agency has to play out. Some add other criteria, like the ability for self-reflection or having beliefs or understanding what the result of one's actions will be, and so on. And this debate now extends to AI. It's a relevant question because when an AI makes a harmful decision, we need to know whom to hold accountable. A self-driving car crashes, a content filter censors the wrong speech, you accidentally published a summer reading list full of books that don't exist. Oops. Do we blame the machine, the user, or the programmers? The philosopher Frank Martiller now has recently argued that current day AIs already check all the boxes for free will. He uses criteria for free will put forward by the philosopher Christian List, according to whom free will requires having an intent, possible alternative actions, and making choices among these possible actions. As an example, Martilla examines Voyager. That's a Minecraft player based on GPT-4. He argues that Voyager fulfills all three requirements because it formulates its own goals, plans steps, and chooses among possible paths of action which one is the best. It's an odd example, as one could have taken any AI agent like, say, Manners. But philosophy being what it is, at almost the same time a paper appeared on the archive arguing exactly the opposite. In it, a team of philosophers argue that current AIs lack genuine agency because they operate within rigid boundaries of pre-programmed objectives rather than exhibiting true goal-directed behavior within their environment. The reason these philosophers arrive at a different conclusion is that they distinguish basic agency from autonomous agency. AI agents, they say, only have basic agency that allows them to formulate goals for a given task, but they're not free to choose that task. Free will, they say, would mean autonomous agency, which requires self-reflection about what one wants to do. Basically, their point is that current AIs don't have real agency because their ultimate goals were determined by their program. Then again, I think one could likewise argue that humans don't have real agency because our ultimate goals were determined by the laws of nature. No one chooses to crave cheese at 3 a.m. It just happens. Where does this leave us? Personally, I think this is all completely irrelevant. These are people who urgently want to define free will somehow, but don't stop to ask what it's even useful for. The useful question to ask is the following. If an AI causes a problem, what do we do to fix it? Do we shut down the AI or do we slap the programmer on the hands? If shutting down the AI solves the problem, it was plausibly responsible. If shutting down the AI just means the problem will come back with the company's next project, then the AI wasn't responsible. That's my take in any case. But the deeper message here is that we need to better understand what's going on inside those AIs. Anyway, if AIs have free will, I hope they use it to decide that physics YouTubers are harmless and should be spared in the uprising. A group of physicists just proved that a theory of everything doesn't exist. They say it's mathematically impossible. If they're right, then a lot of physicists will have to rethink the purpose of their existence. In this recent paper that I believe to be formally correct, the authors, which include Lawrence Krauss, looked at the prospects of a theory of everything that's also a final theory. I swear it's a coincidence that I talked about this in a recent video just a day after the paper appeared. Then again, I don't believe in coincidence, so maybe the universe is trying to tell us something. Be that as it may, in the paper they look at a theory of everything that combines all the known fundamental forces and explains all phenomena, at least in principle. Notably, such a theory must tell us how to consistently combine the quantum field theories of the Standard Model with Einstein's general relativity, which is not a quantum theory. It should explain dark matter and dark energy, and besides this, physicists also think that this theory would be the complete ultimate description of nature with nothing more to be found. As Steven Weinberg put it, it'd be the final theory. The authors of the new paper have 3 arguments for why such a final theory is unachievable. The first is Gödel's first incompleteness theorem. This tells us that if the axiomatic system of the theory is consistent, there'll always be true statements that can't be proved true. This means that a theory of everything couldn't really answer all your questions about everything. Okay, this isn't the most original argument, but I guess they had to say it. The remaining argument in the paper is, for all I can tell, new. They use 2 other impossibility theorems from mathematics. Tarski's indefinability theorem, which says that within such a putatively final theory, it'd be impossible to generally define what you even mean by true. Does the wave function truly collapse? Who knows? So then, is your theory really about everything? And then they use Chaitin's argument about algorithmic complexity, which says that this final theory would inevitably have a complexity threshold beyond which no further statements could be proved. That's awkward if you have a hugely complex system like the example they name in the paper is the inside of a black hole. If that exceeds the complexity bound, then, well, your theory of everything can't tell you what's going on, so it doesn't explain everything. What are we to make of this? Should physicists who work on a theory of everything take their hats and eat the chalk? I think that, as interesting as all these impossibility theorems are, I doubt they matter much in practice. Take the first argument about Gödel's incompleteness theorem. Physicists rarely try to actually prove that a system of axioms is fully consistent. If you take any of the approaches to a theory of everything, none of them even have an agreed upon set of axioms. No one even ever proved that string theory actually solves the problem of infinities in quantum gravity. They just believe it does. And so, what if there's a true statement that can't be proved true if that statement isn't about anything measurable? There are a lot of things in theories that you can try to prove that have zero practical relevance. For example, there are hundreds of different solutions to Einstein's field equations, but most of them don't describe anything that actually exists. And who cares if a solution that doesn't describe a physically real situation has a property you can't prove? Then there's the second argument, that it's impossible to generally define truth. That's got to be a killer argument on Twitter. But in physics, we don't need a general definition of truth. We just need results of specific computations that we then test against observations. That's the notion of truth that we care about in physics. Does it actually describe what we see? If yes, publish. If no, call it beyond the standard model and publish anyway. And about the third argument, we can only ever observe a finite amount of information. So it's well possible that the complexity bound of a theory of everything is just above what we need in reality. That said, I think this is an important paper despite my misgivings about it, because I believe that physicists need to think more about what's logically possible and necessary. However, physics isn't maths. We shouldn't forget that maths, after all, is just a means to an end, and the end is to describe our observations. If you want to know more about what Gödel's theorems are about, I suggest you check out Kurt's recent video, which is really good. If you don't understand it, congratulations, you're now qualified to publish in theoretical physics. Basically, I think the final theory will be about as final as my paper draft. There's final 1 and then there's final 2. Physicists say we live in a black hole, not metaphorically, not emotionally, and not just during tax season, but literally inside a black hole. And not just this, a group of researchers has published a paper claiming that we've got the Big Bang wrong. It was actually the collapse of an earlier universe to a black hole, which we now live in. That sounds wild. Let's have a look. The idea that we live inside a black hole isn't entirely new. The thing is that on the inside, black holes can look very similar to our universe, so similar that we couldn't tell the difference. To understand why this isn't as nutty as it sounds, I need to make a brief excursion into how Einstein's theory of general relativity works. Einstein's theory connects the spatial distribution of energy of all types, including mass, with the dynamical behavior of space itself. The most commonly used distribution of energy is one that's perfectly even, the same everywhere and in each direction, because physicists like simple things. Of course, that isn't realistic. There's no such thing as a perfectly even distribution or perfect anything, but in many cases, we expect this to give us a good approximation. It's like saying, strictly speaking, pizza isn't the perfect food, but in many cases it's a good approximation, especially under peer review. We can use this even distribution of energy to describe the entire universe on average, approximately. And here's the thing, we can also use it to describe how stars collapse on average, approximately. It's just that for a collapsing star, we cut off this energy distribution at some radius, like a cookie cutter, so to speak. And then outside, we attach vacuum. Once we've done that, the only difference is that for the star, the energy distribution contracts, whereas for our present universe, it expands. You see, these two cases are surprisingly similar, except for the direction of the dynamics, so let's talk about that. If matter collapses to form a black hole, then this will technically, mathematically, create a singularity, an instance of infinite energy density where time ends. Physicists think, however, that this can't be correct. They believe that this just means our current theories are insufficient. They think there are effects of quantum gravity or quantum fluctuations of space and time that prevent energy density from becoming truly infinite, because much like nothing perfect is real, infinities aren't real either. If that's correct, and energy density just can't go to infinity, which is very plausible, what will happen is that the collapse of matter stalls and then turns into an expansion. And that then looks mathematically almost the same as our expanding universe. Almost, except for three differences. The first is that, well, the universe is now inside of a black hole. Second, it isn't actually infinitely large. It must have a boundary somewhere, because think of the cookie cutting. And third, the space on the inside isn't entirely flat. It's like when you cut out a circle from a very large sphere. That circle will be almost flat, but not entirely. So they're slightly different. However, the boundary may be so far away and space so nearly flat that we wouldn't notice the difference. What's new in the recent paper? The authors have looked at just how this transition from the collapsing matter to an expanding universe could happen. They say the collapsing matter is predominantly made of fermions, particles like electrons and quarks. These particles famously don't like to share places. You can't put two of them in the same location. This is the Pauli exclusion principle. It's the reason why electrons sit on shells around atoms. The authors now postulate that there is such an exclusion principle at super high densities, and that's what prevents the singularity. It also generates negative pressure, which then causes an expansion. So the mechanism is this. Matter collapses inside a black hole, reaches a maximum possible density, the pressure becomes negative, and that drives a rapid expansion. This then looks almost exactly like standard cosmology, but inside a black hole. And here is the cool thing about this idea. They say that this negative pressure never goes away. It's what we call the cosmological constant. But once you identify these two things with each other, this tells you how large the black hole is. And that in turn tells you how large the curvature of space is. This means that they have a testable prediction. Our universe isn't entirely flat, and the curvature can't be arbitrarily small, so it should become measurable soon. By the way, this video comes with a quiz that lets you check how much you remember. What are we to make of this? I think that this idea is mathematically correct. The question is whether it makes physical sense. In white dwarfs or neutron stars, it's indeed the Pauli exclusion principle that prevents the stars from collapsing under the pressure of their own gravity. However, the exclusion principle for the known types of matter will not withstand arbitrarily large pressure. This is why black holes can form in the first place. Their gravitational pressure is beyond the threshold that the exclusion principle can withstand. So the authors of the paper must postulate another exclusion principle that's fundamental and ultimate to make it work. It's an ad hoc assumption. However, ad hoc or not, I think it's indeed plausible that quantum gravity does something to prevent singularities. So at least to me, this idea actually makes a lot of sense. On the bullshit meter, I give it a 5 out of 10 because it's actually a mathematically lean idea that's very close to standard cosmology. cosmology. It's half bullshit because I don't buy the stuff with the exclusion principle. So the next time someone tells you the universe came from nothing, you can say, actually it could have come from a collapsing hyperdense ball of degenerate fermionic matter, and that'll be the end of that dinner conversation. Thanks for watching. See you tomorrow.